Hello, my wonderful, brilliant, and amazing AP chemists. Welcome to Acid-Base Reactions Part 1. So what we're going to talk about in this video is what happens when we mix strong acids and strong bases. How can we calculate concentrations? How can we calculate pH? All that good stuff. And then we're going to talk about weak acid base equilibria problems. So let's kick things off, starting with our first reaction type. What happens when you mix a strong acid and a strong base? So this reaction is called a neutralization reaction because what happens is things get neutralized. Your acid and your base will react together to neutralize your solution. So they're going to produce in this reaction a salt and water. So that salt is an ionic compound and it's usually remains dissolved in solution when this reaction happens. So if you take a look at our example reaction, we've got nitric acid, HNO3, reacting with potassium hydroxide, KOH. So this is a strong acid and a strong base. We have our acid here, we have our base here. These two things are going to react together. So what's our salt going to be? We'll take the cation from one, the anion ion from the other, throw them together, and we get KNO3, potassium nitrate. That will stay dissolved in solution, and we're going to form water, H2O, as a liquid. All right, so what we really care about in this reaction is like what's actually reacting to produce something. We don't care about our spectator ions. So for our net ionic equation, what's the things that are actually reacting? Well, we've got our hydrogen from our nitric acid reacting with the hydroxide from our base. And this is where what's reacting to produce water, H2O. So there's our net ionic equation for this neutralization reaction. So let's say you take these two things and you mix them together, and we're going to put some numbers on it. You have a 1 molar solution of NaOH, and you're mixing it with a 1 molar solution of HCl. Pause, think really quick. Which ones are acid, which ones are base? Boom, acid, base. All right, so first we want to figure out what's the concentration of the hydronium ion that's in the acid. Well, this is a strong acid, and remember, strong acids completely dissociate. So this thing's going to fully break up into its H plus and Cl minus ions. So if the original solution of our 1 molar HCl is 1 molar, the concentration of hydronium, or the H plus that breaks off, will also be 1 molar. What? Yes. So what's the concentration of the hydroxide ions in the base? Take a look at the base, sodium hydroxide, NaOH. Strong base as well, completely dissociates. So what's that concentration going to be? You guessed it, 1.0 molar. Yes. All right, so this thing's going to totally break up. So if our original solution is 1 molar, our hydroxide, when it breaks up, is going to also be 1 molar. So let's determine the concentration of hydronium and hydroxide in the solution formed when equal volumes of solution A and solution B are combined. So for solution A, let's say we've got our base here. We've got our OH minus and our Na ions floating around. We're going to add to it our acid, which is our H plus ions and our Cl minus ions floating around. Oh, LOL. Here's our acid, here's our base. I feel like I mixed that up when I said it just now. So here's our acid and here's our base. Hydroxide plus our hydronium floating around in solution. So when these things are equimolar, that means they have the same same number of moles. We're adding the same amount of each of them. We're adding the same volumes. They have the exact same concentration. When we mix these two things together, we're going to completely neutralize the acid and the base. So there's the same moles of hydronium that there will be of hydroxide, and they react according to our net ionic equation back up here in a 1-to-1 mole ratio. So that means that they're going to completely neutralize each other. There's nothing left over because we have the same amount of both of them. So in our final solution, we'll have our water floating around, and then we'll have our spectator ions, but no more free hydroniums, no more free hydroxides, because this thing is completely neutral. So what's the concentration of these things when they've mixed? 0. There's nothing left. 0 for both. They've completely neutralized, so they have no concentration left. So if there's no free hydroniums and no free hydroxides, what should the pH of our solution be? Well, if there's no acid or base, we're going to sit right at that neutral line. So our pH must be 7 because we're in a neutral solution. Okay, so let's consider a different scenario. Let's say we have an excess of either hydronium or hydroxide ions remaining in the solution after an acid-base reaction. The solution's not going to be neutral. Now you have excess acid or base floating around in your reaction chamber. So we can calculate which ion will be in excess from starting or diluted hydronium or hydroxide concentrations before they actually react. So let's take this scenario right here. You have your initial concentration of your hydronium is greater than your initial concentration of hydroxide. So which one's going to get used up first? Your hydroxide, because you have just less of it available. So if we want to calculate pH, what we can use is, or what equation we can use to help us is first finding that concentration of the excess hydronium. So how much hydronium will we have left over? We're going to call it concentration of H3O plus excess. To figure it out, we take our starting concentration of the hydronium and we subtract out the concentration of our hydroxide. That's going to tell us how much hydronium we have left in excess. Alternatively, what would happen if our hydronium gets used up first? It's our limiting reactant. If our concentration of our hydroxide is in greater quantity, then the exact opposite equation will be true. The concentration of OH excess, because now we'll have a slightly basic solution, is equal to the concentration of our starting hydroxide, subtracting out the concentration of our starting hydronium. All right, so from here, what we only have is our concentration of the acid or the base, so we can't directly calculate pH from this, but we can use those numbers to then throw into the pH or pOH formula. So let's get an example of this to see how it works. Calculate the pH of the solution resulting from mixing 30 milliliters of 0.4 molar nitric acid with 70 milliliters of 0.2 molar sodium hydroxide. So before our reaction happens, we're mixing these two solutions, which means we have to do a dilution equation really quick to figure out what the new concentration will be once mixed before the reaction happens. So let's start out with doing this for our hydronium. H3O plus. To do the dilution, we need to use our favorite formula, M1V1 equals M2V2. And what we're trying to solve for is our new concentration, our new molarity. So M2 is equal to M1V1 divided by V2. So let's calculate this out. We've got a strong acid and a strong base, so they're going to completely dissociate. So we know the concentration of our acid is equal to, or the concentration of our hydronium is equal to that concentration of the acid before we mix. So we're going to start out with 0.40 molar. And then, let me put it in our traditional format. So here's our M1. We're multiplying this by our V1. So our original volume is 30 milliliters. And then once we mix these two solutions together, we have 30 milliliters of one thing, 70 milliliters of the other. So our final volume is 100 milliliters. So here my units cancel. And when I throw this into my calculator, I end up with a concentration of H3O plus as 0.12 molar. I'm actually going to write a little ST next to this to say this is our starting concentration, of our hydronium. Okay, now we're going to do the exact same thing, but for our hydroxide. So starting hydroxide concentration, while we started out with a 0.2 molar solution that we had 70 milliliters of, and once I mix them, I'm getting 100 milliliters of total volume solution. So throwing this in my calculator, I get 0.14 molar. So this is the concentration of my starting hydroxide. So now let's compare. 0.12 compared to 0.14. This is greater. So what does this actually mean? Therefore, the HNO3, Therefore, HNO3 is our limiting reactant. This thing's going to run out first. So which formula are we going to use? Well, we know that we're going to have excess hydroxide left over because our nitric acid is going to run out first. So we're going to make use of this formula up here. Okay, so this formula says our excess hydroxide, because we know we're going to have this left over since nitric acid is limiting. We take our 0.14 molar starting concentration of hydroxide. We subtract out our 0.12 molar starting concentration of hydronium. And what we're left with at the end is 0.02 molar. So this is our excess hydroxide ion concentration. So if we want to find pH of this formula, we have to first think, okay, is there a formula that takes me directly from concentration of hydroxide to pH? No, but I can find pOH. So recall that our pOH formula is equal to the negative log of our hydroxide ion concentration. So I can plug this in to say pOH is equal to negative log of 0.02 molar. So this is going to end up with a pOH of 1.7. All right, now what's the relationship between pH and pOH? Well, we know it's measured on that scale up to 14. So pH plus pOH is equal to 14. If I want to solve for pH, I can take 14 and subtract out my pOH. So my final pH of this solution will be equal to 12.3. Yay! All right, so this is mixing strong acid, strong base. There's two practice problems on the next page. I want to walk you through the first part of this one right here because it's a little bit tricky. So keep in mind with this example that we just did right here, we're working with nitric acid. Nitric acid is what's called a monoprotic acid, meaning it has monoprotic, one proton, it's got one hydrogen. If you have an acid like sulfuric, which is going to show up in this problem, this is called a diprotic acid. And they're a little bit trickier to work with because you're not just dissociating into forming one hydrogen ion, you're dissociating into forming two hydrogen ions. So let me write you out a couple reaction equations really quick. So you've got H2SO4 and you're diluting it with some water. So you take your sulfuric acid, you add water to it, and what's this going to form? Well, here's your acid, here's your base. So sulfuric acid is going to donate one of its hydrogens to water to form H3O plus. Here's our conjugate acid. And what's left over? HSO4 minus. Okay, sounds good. We've got our conjugate acid right here. We've got our conjugate base right here. But that HSO4 can still lose another proton. All right, so now I'm going to take at HSO4, and let's say this thing continues reacting with water. What are we going to make? Well, that HSO4 is actually still an acid. It still has a hydrogen to donate. So it's going to do it again. And that's going to form SO4. It's going to lose its hydrogen. It's going to donate it to the water again to form H3O plus. So now you've got this polyatomic ion you should recognize, sulfate, right here with a 2- charge. So if we write a full equation for this, what we see is that we end up with H2SO4 plus 2H2O yields 2H3O plus SO4 2-. So what this is showing is that when this reacts, for every 1 mole of sulfuric acid, you're producing 2 moles of your hydronium ions. So this is actually going to take a little bit of extra work when we do our dilution. We can't just use a classic M1V1. What we're actually still doing is a dilution. But the way that I'm going to show you how to break it up is a little bit more like how we see our traditional stoich in our dimensional analysis. So let's actually get into the problem, figure out what we need. Calculate the pH of a solution resulting from mixing 50 milliliters of 0.2 molar H2SO4 with 100 milliliters of 0.4 molar NaOH. Okay, so to calculate our starting hydronium ion concentration, first think about what's its initial concentration before any dilution happens? 0.2 molar. I'm going to write it out as moles per liter, like this. So this is still a strong acid. It's going to completely dissociate. So that means that our hydronium ion concentration is 0.2 molar. But for every 1 mole of sulfuric acid, we're producing 2 moles of hydronium ions according to this balanced equation right here. So the other way you could do this without actually writing out the stoich is just knowing like, oh, it's got 2 hydrogens, so I'm going to release double the amount of hydrogens when this thing completely dissociates, and you could just double the concentration to be 0.4. But I want to show you where it's coming from in the stoich so that way you know why I'm using the numbers I'm using. It also gets your units to cancel too. Okay, so what we have here is now still moles per liter, right? And we know in that M1V1 equals M2V2 formula, if we're solving for this, all we have to do is divide this side by V2. So rather than rewriting this out, I'm just going to build this into my already working dimensional analysis. So I've got molarity here. What's the initial volume of my acid solution? 50 milliliters. M1. What's my V2? What's my final volume after mixing? 50 milliliters plus 100 milliliters, so 150 milliliters. So it's still M1V1 divided by V2. I've just broken it out into the stoich step to include the fact that now I can cancel out these moles of H2SO4. I really should have written H2SO4 here, sorry. To account for the fact that it's a diprotic acid. So at the end of this, when you plug it into your calculator, you end up with a H3O plus concentration of 0.1333 molar. Okay, so I'm going to have you pause the video here. The hydroxide ion concentration is the exact same setup as the one from before. That one's just a straight up dilution, no tricks. And then figure out what your final pH is going to be. Pause the video, do this problem, come back and check your answer, and then we're going to do that last one where I'll set you up for this one too, okay? All right. Pause. Do your calculation. Come on back. And you should have ended up with a pH of 13.13. If you didn't, check my answer keys, see where you went wrong. The last thing that I do want to remind you of when we're doing pH, it came up in 4.1, our first assignment, but when you're doing sig figs for pH problems, only the numbers after the decimal point are significant. So here, this is still actually only 2 sig figs. Oh, actually, sorry, that's only 2 sig figs, but you need 3 for this problem. So you should have had 13.125. There we go. So this is your final answer. This now has 3 sig figs, which is exactly what you needed for this problem. All right, moving on. Mass of NaOH must be calculated from 500 milliliters of a solution of 0.02 molar HI to obtain a solution with a final pH of 2.5. Okay, how are we going to think through this problem? How are we going to start it? All right, start with your pH. If we take a look at pH of 2.50, what is that actually telling us? Well, it's telling us that our final solution is acidic. So what does that mean about which ion is in excess concentration? It has to be the hydronium. Because our because our pH is acidic, we must be having excess hydronium in that solution. So what I can start with is actually finding my excess concentration of hydronium. I know that to calculate the concentration of hydronium, I can use the 10 to the negative pH formula. So the concentration of hydronium in excess, pen's freaking out, in excess is equal to 10 to the negative 2.50. So when I throw this in my calculator, what I end up with is 0.00316 molar. So that's the concentration of my excess hydronium. Okay, cool, great. But if I want to figure out mass of NaOH, I need to know something about my hydroxide, right? So let's take a look at this formula again. If I can get to my... let's take a look at this formula. If I can get to my concentration of hydroxide, I can figure out the mass of NaOH I need. So I know that my hydronium is in excess, so this is the formula that I want to use. So I'm just going to duplicate that and drag it down real quick for us to use. Right down here. All right, so I know this. I've got that down already. I need to know this, which means if I need to solve for that variable, I also need to be able to know the concentration of my initial hydronium, which I do. All I got to do is look at this. The initial concentration of my hydronium is 0.02 molar because HI is a strong acid. That's going to completely dissociate. Why do I not care about this number right now? Because in my solution, all I have is 500 milliliters of a 0.02 molar solution. So the concentration of my hydronium is still 0.02 molar. I only care about that 500 milliliters because that's just telling me that's how much I have, and I'm going to add some NaOH to it at the end for a 500 milliliter solution in total. So I don't care about that number right now. All I care about is the fact that this is going to completely dissociate to get me the ions that I need. So my starting concentration of hydronium is 0.2 molar. Okay, so let's rearrange this equation to get the one we want. I am going to add concentration of hydroxide to both sides, and I'm going to, at the same time, subtract out excess concentration of hydronium. So when I do that little algebra step, this is the formula that I end up with. Starting concentration of hydronium, subtract out excess concentration of hydronium, and now I can solve for my starting concentration of hydroxide. So I know this to be 0.02. This is 0.00316. And so my hydroxide starting concentration, when I throw that in my calculator, will be 0.0168 molar. Woo, yay, great. All right, but what am I asked to solve for? Mass. All right, no big deal. I can do that. So what I'm going to figure out now is that I have 0.0168 moles of NaOH per liter. So at the end of this, I need to end up with grams of NaOH. So how can I get there? First things first, I can get from moles to grams by using molar mass. So the molar mass of sodium hydroxide is approximately 40 grams per 1 mole. All right, but I just need grams. I still have that pesky liters to deal with. Oh, but wait, I know how much volume my final solution has. It's 500 milliliters. So I will have 0.500 liters of solution. So when I go through and check my canceling, liters, yay, moles, woo, I'm left with, boom, just grams. Exactly what I wanted. So at the end of this, I plug it in my calculator and I need 0.34 grams of NaOH in order to make a solution with the pH that I want. Yay! All right, so I know this video is going to end up being kind of long, but I'm just going to do it all in one go. I'm going to have you, if you were absent on this day, use my answer key, check my notes on Canvas to work through this acid reaction section. I'm going to move on just to weak acid base equilibria because this is going to take a hot second. All right, weak acid base equilibria, here we go. So let's say you have a weak acid and you add it to a base. What's the issue with that? Well, it doesn't completely dissociate. So that means that a weak acid and a base are going to form an equilibrium system. So you can see our general net reaction right here. You have some weak acid, we call it HA. We're reacting it with water, we're adding it to water, which is going to act like our base here. So the HA is going to donate its proton, the acid will, or the base water will accept that proton, and we end up with A- and H3O plus in an equilibrium system. So let's see what that looks like with an actual acid. So this one right here is acetic, CH3COOH. The reason why it's typically written out like this when we're talking acid base is because it's going to lose that hydrogen right there. So it's kind of just a helpful way of saying which hydrogen is going to leave. Oh, that one, it's on the end. We will talk about acid structure next week. That'll help us do a little bit more digging into like, oh, which hydrogen will it actually lose? But for now, just know that's why it's written like that. So here's our acid reacting with water as our base. So this thing's going to lose its proton, donate it to form CH3COO minus. This is the acetate ion. And then water is going to accept that hydrogen to form H3O plus. Okay, so this is an equilibrium system, which means that it has a KEQ, an equilibrium constant expression. But remember, when you start dealing with specific equilibria, you get like specific little subscripts to represent what equilibria you're dealing with. So like for solubility, we dealt with KSP. For gases that had pressures, we used KP. So here, same thing, we're going to use Ka. And what we call it is the acid ionization constant. But it's just an equilibrium system. It's just an equilibrium constant. So we write it the same way we do the others. Ka is equal to the concentration of our products, A minus H3O plus, over the concentration of our reactants, HA. For the specific reaction equation that I have written here, you would write Ka is equal to our acetate ion times the concentration of our hydronium divided by concentration of our acid, CH3COOH. Okay, so to determine the strength of our acid, we can use our Ka value or we can use our pKa values. So for those of you who don't remember pKa, go back to the 101 notes, go back to the old pH video that I've posted to find out like where that pKa number comes from. But what you need to know is that it's basically like a pH thing. So strong acids will have high Ka values and low pKa values. So the pKa formula is just like the pH formula. To find pKa, you take the negative log of Ka, and to find Ka, you raise 10 to the power of negative pKa. All right, so for weak base with an acid, I'm going to take away the word strong, sorry, just weak base with acid. You have base B reacting with water to form an equilibrium system because it doesn't completely dissociate. So you get Hb plus OH minus. So here's an example for you. You have methylamine reacting with water to form its equilibrium system. So methylamine is our base, which means it's going to take a proton from water to form CH3 NH3 plus because it's gained a proton. And water is going to lose one of its protons to form OH minus. So same way for acids, we have an equilibrium system for our base here, and we call it our base ionization constant, represented by K lowercase b. So Kb is equal to the concentration of your products over your reactants in general. For the reaction that I just gave you above as our example, CH3 NH3 plus, one of our products, times concentration of OH minus, our other product, divided by our base, concentration of our base, CH3 NH2. So exact same thing here. To determine the strength of a base, we can use Kb or pKb values. Strong bases will have high Kb and low pKb values. That's what we get for not proofreading well enough. Okay, let's practice. So write a Ka or Kb expression for the following acid-base equilibria. Identify conjugate acid-base pairs. And here's my pro tip again. For acids, hydrogen is typically taken away from the beginning of the formula. This one, it was taken away from the end of the formula. Don't come for me. It's just how it's written. And then for bases, the hydrogen is typically added at the end of your formula. So practice trying to write out Kas, Kbs for those AB formulas. And then on the next page, you have extra practice problems where you're predicting products and then also writing Ka, Kb, and finding conjugate acid-base pairs. So do those 4 practice problems, check the answer key, come on back. Yay! Okay, so now we're going to talk about calculations. Here we go. Everyone take a deep breath. We're going to do some rice tables. Yes. So these are equilibrium problems, which means if we want to calculate equilibrium concentrations, we got to use rice tables to help us out. So first problem, determine pH and pOH of a 1 molar solution of hydrofluoric acid, HF. And we're given a Ka value of 7.2 times 10 to the negative 4th. Okay, awesome. So let's start out by thinking what our initial concentrations are. So we've got our HF. This thing is going to have an initial concentration of 1.0 molar. We are told that, so we're going to put that into our rice table right there. We will not initially have any hydronium or fluoride ions, so we're going to put a concentration of 0 for both of these. What about for our water? It doesn't matter. What? Oh my God, water always matters. It's so important. But think about what actually is being represented here in our equilibrium system. If we're talking about Ka, our acid ionization constant, this is equal to the concentration of our products, H3O plus times F minus, over the concentration of our aqueous reactants, HF. We never include solids or liquids in our equilibrium constant expressions, so we don't care about the water at all. So we're just going to cross it off from our rice table. Yes, you do still need to write it. Okay, so in this system, what's going to happen to our HF over time? Well, we're going to lose some of it. How much? X. We're going to gain some hydronium plus X, and we're going to gain some fluoride plus X. Everything's in a 1-to-1 ratio here, 1-to-1-to-1 ratio here. Yes, love to see it. So what's our final equilibrium concentrations? Well, we started out with 1.0 molar for our HF, and we're losing some of it here. At the end, we're going to have X concentration of hydronium and X concentration of fluoride. All right, here's our best friend again. We have something that's a little complicated to do some algebra with, and we do not want to do complicated algebra. So what we're going to do is we're going to assume X is small. Okay. Awesome, great. When we do that, we end up with the fact that X is like gonna dissociate, but it's so negligible, the concentration is not gonna change that much because it's a weak acid, that we're just gonna basically call it 1. Okay, so let's go back to our Ka expression. We know that Ka is equal to 7.2 times 10 to the negative fourth. Awesome. Concentration at equilibrium hydronium is X. Cool. Concentration of fluoride is also X. Oh my God. X times X is X squared. Yes. Love to see it. We assumed that X is small, so what's the concentration of our hydrogen fluoride? No, what's the concentration of our hydrofluoric acid at equilibrium? Just 1. Ooh, love this math for me. 1 times 7.2 times 10 to the negative fourth, 7.2 times 10 to the negative fourth, super cool. And I'm such a genius that I can do square roots in my head. Just kidding, I did this ahead of time. So I'm going to find that the X concentration, the X value is equal to 0.027 molar. All right, so what does this actually represent? Why do I care about this? Well, in this problem, I'm trying to determine pH and POH, right? So all I really care about right now is the fact that this is equal to the concentration of my hydronium ion. So if I want to find pH, pH is equal to the negative log of the concentration of my hydronium ion, which I just solved for. So it's equal to the negative log of 0.027. Plugging this in our calculator, we get a pH value of 1.57. Yes, love. Cool. Moving on. POH. I know that POH is equal to 14 minus my pH value. So what I end up with is a POH of 12.43. Box it. Donezo. Yes. But I am going to remind you of the check approximations that you need to know. This is something that I very strongly recommend that you do, especially on the AP test when you're doing these ice table calculations. You want to make sure that you can actually say that X is small enough to be counted. So remember, we're looking for something less than 5% of our original concentration. So let's do a quick check just to make sure we're good. So check approximation. This is also just a good reminder of how to do these since we haven't done one in a little bit. So what we can say is our percent change in concentration is equal to the change in concentration divided by our initial concentration times 100%. So our change in concentration is equal to the X value because this is how much we're changing by, which came out to be 0.027. Our initial concentration of our acid was 1.0 molar, and then I multiply by 100 to turn it into a percentage. When I do that, I get 2.7%. So this is my percent change in concentration. This is less than 5%, so what we can say is our approximation is valid. So we're allowed to say that X is significantly small enough that it's not affecting our algebra. All right, you try this one, but this time you're doing it with a KB. Oh God, no, KB, that's so scary. It's the exact same thing. The only thing different here is that you're dissociating a weak base, so you need to use that KB formula, which is just your hydroxide instead of your hydronium. So do this practice problem, and I think you actually can do all of these practice problems. Yeah, do them all. Do these 3 practice problems and then check in with the answer key, then come on back. Okay, hi everybody. I hope you had such a great time with those equilibrium problems that you definitely paused the video for, did completely, and checked the answer key, and then came back for. Now we're going to talk about percent ionization. So this is also called percent dissociation. So percent ionization of a compound is just a measure of how much a compound ionizes or dissociates into its ions in solution. So for strong acids and bases, percent ionization is 100%. The whole thing completely dissociates. It breaks apart completely, 100% dissociated. But for weak acids and bases, percent dissociation, you got to calculate using a Rice table. The equation below tells you how to find percent dissociation. So it's amount dissociated divided by initial concentration times 100%, where amount dissociated is your X value in your Rice table. So let's do an example. Calculate the percent dissociation for 0.22 molar solution of this base right here. Kb is equal to 5.6 times 10 to the negative fourth. Okay, how much is dissociated? We got to solve for our X value first. So let's start out by writing a Rice table. So we have our base C2H5NH2 aqueous. We're adding it to water, and this thing is going to form an equilibrium system to make hydroxide and a conjugate acid. All right, here is our Rice table. Okay. So remember, we don't care about water at all in this system. Well, we don't care about how it's affecting this system. So I'm just going to go ahead and cross that section out. So let's start out with our original concentration of our base. So we're told that it's 0.22 molar. It's going to change by some amount. How much? We're going to call it X because it's a one mole in this system. So at equilibrium, we're going to have 0.22 minus X. We start out with no concentration of our conjugate acid or base, and then we're going to change by X amount in the system, and we're going to be left with X at the end. So here we're going to once again make the assumption that X is small. So small that it's negligible. Okay, so if we want to find percent dissociation, we got to start out by finding our X value, how much has changed. So let's write out a Kb, a base ionization constant for this reaction. We have our concentration of our products, OH, C2H5NH3 plus, over our original base, concentration of our original base, C2H5NH2. All right, so concentration of our conjugate acid and base are both X. So we're going to say that Kb, which we're given the value of 5.6 times 10 to the negative fourth, is equal to X squared over the concentration of our original base, which we said X was so small it's negligible that it's essentially equal to 0.22. So when I solve for this, I get an X value of 0.011 molar. So this is the concentration of our hydroxide in the equilibrium system. So to find percent dissociation, how much did this thing dissociate? I take my amount dissociated, which is 0.011. I divide it by my initial concentration, which was 0.22, and I multiply it by 100%. When I do this, I get my percent dissociation is equal to 5.0. So this tells us that 5% of our base dissociated into solution. All right, why don't you try the last practice problem right here? Pause the video, do it, check the answer key, and come on back for a super fun challenge problem. All right, friends, welcome back. Here we go. I love saving the challenge problems to the end because at this point you've watched the whole video and you're like, oh my God, Miss Lambert, I'm so exhausted. Let me just be done. And I'm like, no, let's do another one. Okay, here we go. So a solution of fluoride ion F minus has a percent ionization of 8.12 times 10 to the negative fourth percent and a pH of 8.271. So basically what we're asked to do is write the chemical equation and an equilibrium expression. We're asked to calculate the hydroxide ion concentration, calculate the original molarity of the fluoride in solution, and determine the Kb value for fluoride F minus. All right. So I'm actually going to start out with just developing a rice table because we know we're going to need it. So we're going to write our chemical reaction equation first. So we have our fluoride ion, a solution of fluoride ion. This means we've got F minus aqueous just floating around in solution. So it must be in water. So we've got our fluoride in water. So this thing is forming an equilibrium system as it goes back into its conjugate base and conjugate acid. So fluoride here is a base. It can accept a hydrogen. So the water is acting like our acid, which will donate the hydrogen to the fluoride. So when it does that, water is going to form OH minus, and we're going to form HF as our conjugate acid. All right. So here's the start of our rice table. We know that for this reaction, our Kb is going to be equal to concentration of our products over concentration of our original base. And we don't care about water in this system. Cross. Okay, so how do we start? Well, we know that we're going to need to calculate hydroxide ion concentration. We know we're going to need to calculate original molarity and the Kb value. That's kind of a tall order. So let's take a look at what we're given. That'll help guide us in the direction we need to go. We're given a percent dissociation or a percent ionization, and we're given a pH value. Ooh, pH. I can do something with that. If I know pH, what I can get to is a concentration of an acid. Cool. That's great. So I know that pH, or actually, I know I want to get to concentration of an acid, so I know that concentration of hydronium ions in solution is equal to 10 to the negative pH. Cool. All right. So 10 to the negative 8.271 is going to get me a hydronium ion concentration of 5.4 times 10 to the negative 9th. Okay, so if I want to find hydroxide ion concentration, how do I do that? Ooh, another thing that I know that the concentration of hydronium times the concentration of hydroxide should always get me 1.0 times 10 to the negative 14th. Cool. So I have one number. I have two numbers. I know this value. So I can solve for this last one right here. So concentration of hydroxide ions must be equal to 1.0 times 10 to the negative 14th divided by my concentration of hydronium, which I said was 5.4 times 10 to the negative 9th. Yay! So when I get this number, I plug it in my calculator, I get a concentration of hydroxide to be 1.5 times 10 to the negative 6th molar. So what does this actually represent? Well, at equilibrium, this is my concentration of hydroxide. So I can plug this number into my rice table. At equilibrium, this is my concentration. So I'm going to plug that in. Oops. I'm going to plug that in right here. So at the very end of this system, I end up with this concentration of hydroxide. But hydroxide and HF are in a 1-to-1 ratio, which means I also end up with this concentration of HF. And I know that initially I should have 0 concentration of my hydroxide and my HF, my hydrofluoric acid. So how did I have to get to that number? Well, I had to add this exact number to my system. So this is my change in concentration. I added this much to each of these systems, which means I'm also going to change by this much when I subtract out my H minus, my fluoride ion. So this is my change value. I'm adding for my products, and I am subtracting for my reactants. Okay, cool, great. Now, if I want to find my initial fluoride ion concentration, I still got some more work to do. So let's think about what else we're given. We used our pH, cool, but we have that percent dissociation. So what does percent dissociation equal again? So percent dissociation or percent ionization is our amount dissociated divided by our initial concentration. Ooh, there's something I want. I want initial concentration. Do I know the other two values? Can I get there? Yes. My amount dissociated is my change number. It's my final equilibrium. So I changed by 1.85 times 10 to the negative 6 molar. That's my amount dissociated. Do I know my percent dissociation? Yes, I'm given that in the problem. All right. So do some quick little algebra, and I end up with my amount dissociated divided by my percent dissociated is going to equal my initial concentration. Dope. Cool. So I'm going to say concentration initial is equal to my amount dissociated, 1.85 times 10 to the negative 6th. And then my percent dissociation is given as 8.12 times 10 to the negative 4th percent. But I need to convert that number to not a percentage. So I'm going to divide by 100. And when I do that, I move my decimal place over twice. So I end up with 8.12 times 10 to the negative 6th. 10 to the negative 6, 10 to the negative 6. Yes, we love when the orders are the same because then all we have to do is divide our coefficients. So our initial concentration, when we plug this into our calculator, is equal to 0.228 molar. Another number I can plug into my Rice table. My initial concentration is 0.228 molar. So now I can find my equilibrium concentration. Okay. So 0.228 minus 1.85 times 10 to the negative 6. 10 to the negative 6th. That's insanely small. That's a super incredibly small number. So essentially, what we're finding out here is that our x value is small. Our change value is small. So if that's true, it's essentially negligible. So what I can say is my equilibrium concentration is not going to change very much. It's basically still equal to 0.228 molar, which is cool. But now I've got equilibrium concentrations of everything. And if I've got equilibrium concentrations of everything, I can plug into KB, which is the last thing that I needed for this problem that has taken so much of our lives. But it's been a good time, I hope. All right, KB is equal to concentration of HF, cool, 1.85 times 10 to the negative 6th times concentration of OH minus, which is the exact same thing. So we're going to square that bad boy. And then we're going to divide out by our equilibrium concentration of the fluoride ion, which we said was essentially 0.228. And when we solve this, we get KB is equal to 1.5 times 10 to the negative 11th. Box it, box you, put a smiley face that looks crazy because we have finished the problem. Yay! And the packet, double yay. All right, see you guys later.